You how to solve linear and integer programs using the computer software um, MathProg. First step is to go to this website. You can find it by searching on Google for MathProg online. All right, so first let's take a look at the examples. So here's a simple linear program in two variables. All right, so anything with a dollar sign is ignored. Any line that starts with a dollar sign is ignored. First step is declare two variables. So x and y are your variables. Every line has to end with a semicolon, just like a Java program. Okay. Next, we have our constraints. So that, and I don't believe you need to say so that for each one. I think this can be left off. But you need to give your constraint a name usually. So this is the name of the constraint. It's constraint A with a colon. And then this is the actual constraint. Notice that to do a less than or equal to, you do less than and then equal to. All right, so we have our three constraints for our linear program. Next, we have our objective. So you want to put the word maximize here. If you leave it blank, I believe it'll minimize. So that's usually what people do. So maximize has to be there if you want to maximize your problem. And the objective is z. So you're saying z is equal to 3x plus 4y. Notice that you have to say 3 times x, 4 times y. You can't just say 3x without the star because it won't read it as multiplication. So 3 times x plus 4 times y equals z. And then we want the program to solve this linear program and end. All right, so let's click the solve button. And you see instantly we have our solution. The way that it's solved this is with the simplex method. The objective is 34, so z is the maximum z value. There's two continuous variables, they're non-integer. And if we look at the output, the variables, so the solution is x is 6, y is 4. We'll learn about this later on in the course. And this is the log file. This is what would get printed out to the screen if you ran this on your computer, which you can download. It's called GLPK Simplex Optimizer. All right, so here's the output. An optimal solution was found. The objective value is 34. All right, let's go to another example. Up here is the actual linear program the way that we would write it. All right. Giappetto's workshop. So in this case, we have a simple integer program. So we're saying that x1 is a variable greater than or equal to 0, and it has to be integer. And x2 has to be integer. So this represents the number of soldiers and trains. And we want to maximize our profit. So this is z. Instead of z, you can just use the word profit. 3x1 plus 2x2. Here's our constraints, our finishing, carpentry, and demand. This is slightly different from our books example, but it's almost identical to the one we did in class. Okay, so we have our three constraints. Solve it, and then this is some programming code here. What this does is it prints out it prints out the variables x1, x2, and the profit, and it displays the constraints: finishing, carpentry, and demand. So let's run it. Solve. Let's look at the dashboard first. Objective value profit is 183. Notice this is an integer optimization. We have two integer variables, 4 constraints. It's probably counting some of the constraints as these as constraints, but let's see. All right, so look at the variables. The solution is 23 and 57, so x1, 23, x2, 57. Double check, it's an integer variable. What this is, the relaxed, this would be if we left off the integer. So let's leave off the integer and just make them regular variables that are greater than or equal to 0. Let's solve it. See, this is the linear program. If you ignore the fact that x1 and x2 have to be integer. Putting them back in. Solve it again. Okay, look at the here are your constraints. Here's the log file. All right, so this is what actually occurs on the computer. All right, so it solves the linear program first, and it gets 183.52. That, of course, is not integer. So now it starts searching for integers. And we'll learn about this pretty soon. And it solved the answer. Though in this area, it's not printing out the values of the variables. Let me try it one more time. All right. Okay. Oh, here's what I was looking for. So I was looking for the output. All right. So this output is from this part here. This is after the linear program, integer program is solved. It does these commands. It's actually a full programming language, and we're going to learn a little bit about it. So display x1, x2. So x1's value is 23. x2's value is 57. Profit's value is 183. And then it displays the value of the finishing constraint, carpentry constraint, and demand constraint. It basically plugs in x1 and x2 into the left-hand side and tells you how close you are to violating the constraint. So as you can see, it's pretty close. It got to 99.5 and up to 100. All right. So that's the basics. So our goal now is to solve the post office problem using MathProg. So this time we need 6 variables. 7 variables actually, all greater than or equal to 0. So let's change this. This is page 73 of Winston, Operations Research. And this is the post office problem. All right, so let's get rid of this. All right, so we need some more variables. We need 7. So let's copy and paste it. All right, so let's see, x1, x2, x3, x4, x5, x6, x7. Right. Our objective is, let's just call it Z. It's the number of employees. And we want to minimize Z. All right, so what do we have? We have x1 plus, so x1 plus x2 plus x3 plus x4 plus x5 plus x6 plus x7. And now we have our constraints. So I don't think you need the such that. So I'm just going to say A. So it's x1 plus x4 plus x5 plus x6 plus x7 greater than or equal to 17. And let's just copy and paste this, and we'll keep modifying it. We have 7 days. All right, the next one is x1, x2. And then we go to x5, 6, and 7. The next one is x1, x2, x3. And x6 and x7. Don't forget about the right-hand side. And the next one is x1, x2, x3, and x4, plus x7. The next one would be x1 to x5, 2, x3, x4, x5, and then x2 to x6, and x3 to x7. Now the right-hand side's 13, 17, 13, 15, 19, 14, 16, 11. display x1, x2, x3, x4, x5, x6, x7, and z. And finally, let's change these: B, C, D, E, F, and G. All right, let's hope we didn't make any mistakes. It looks like I x1, 2, 2, 3, 4, 5, 6, 7. All right, so let's solve it. And I think we have it right. Here's the solution. And checking the textbook out, solution is 23. The book solution is 4426043. Notice it gives us a different solution. There are actually a few different solutions, not just one. There are programs that can actually find all the solutions in about a second. Notice if we took off the integers, well, before I do this, let me show you the log file. So here's the log file. So this generates the linear program. It solves it with the simplex method, which we're going to learn how to do by hand pretty soon. All right, it found an optimal solution, 22.3333. So that's what the book also gets. But that's the linear program solution. That's not the integer. Now it has to find the best integer solution out there. So it searched through it. It looks through it through a tree that it forms, and we'll learn about this tree probably next week. And eventually, it proves that 23 is the optimal integer value. And this particular one was solved very fast, 0.072 seconds. All right, so let's just see if you take out the integer, you'll get that answer of 22 and a third. All right, so once again, I'll slowly go. We'll take a look at this. So this is it, and this will allow you to model complicated problems for homework and then actually get an answer, seeing if you modeled it correctly by whether or not you can get the optimal solution correct. Right, there's only one unique z value for the optimal solution, but there could be many x values, but there's only one z, that's the 23. All right, so to conclude this video, I'll show you some examples of some of the complicated things we'll look at, but we have to learn how to program here. We have to learn about sets and how to use sets in this program. So if you want to take a look at the examples, look at the sets, and parameters is also very important. Keeping track of all the different data. All right, so let me show you a few interesting problems. So, traveling salesman problem with time windows. Basically, what you have here is a salesman has to arrive at certain locations within certain time windows. In this case, it's an airplane, and these are airports. These are the latitude and longitude. They could be ships for our purposes. And Let's see. Let's try to find the time windows. Oh, here are the time windows. They have to arrive at Atlanta between 8 a.m. and 2400. They have to arrive at Boston between 8 a.m. and 9 a.m. They have to arrive at JFK between 1800 and 2000. And these are this is the location of the airport. All right, so let's solve this. It actually takes a minute, as you can see. This is an integer program. This is a hard integer program. It took 2.682 seconds of computer time. Though there are faster solvers that will do it much faster. If we look at the output, here's the timetable. So depart Atlanta at 7.10 hours, I believe, and arrive at Boston at 9. And this would satisfy the time windows. The plane would arrive at the various locations when it's supposed to. Scheduling. We'll take a look at the Jesuit volunteer program at some point. This is actually a bit complicated. 7 people in a house, broken down the chores into 4 major sections: kitchen, bathroom, common area, and trash. The trash is the only task that needs only one person to accomplish. The other 3 tasks have 2 people assigned to them. Each person needs to rotate through each task twice and trash only once. The assignments rotate each week. Each person needs to have a new partner each week, and no person can have more than 1 task in a week. So this is the formulation of the integer program. This is a bit more complicated, and we'll learn how to do this probably in a couple weeks. But you need a variable with triple subscripts, VTW. And basically the idea is it's equal to 1 if volunteer V is assigned task T in week W. That's what the VTW. So really what this is saying is you have V is the number of volunteers, 7 volunteers. T is the number of tasks, I believe, number of tasks, T's and tasks. So there are 4 tasks, and the weeks are from 1 to T. T is 7 weeks. So 49 times 4. So as you can see, almost 200 variables are declared with this one line. Once again, there's 196 variables are declared just with this one line. And that's the real power of this kind of system. All right, so let's solve it. It's taking a minute or 2 to think. This is actually a complicated problem. And this is the schedule. All right, so this is when people have to take out the trash and all. You want to see the output, the log, see how long it takes to find it. So actually, it took 7.198 seconds. All right, so to show you how you could do this on a, well, you can solve this with other solvers, and it would solve this probably in a 100th of a second. So this is a very slow solver. All right, so this concludes this this first video, and in class we'll learn how to the hard stuff, how to actually program these complicated variables and constraints in. And we'll eventually, hopefully, go through this program and understand it.